Welcome to the course on Fundamentals of MIMO Wireless Communications. Till now we have covered the diversity gains achievable in a MIMO communication, in which we have seen receive diversity, transmit diversity, as well as diversity that can be obtained when there are multiple antennas both at the transmitter side as well as the receiver side. With this, it's time now that we move forward and try to understand the capacity gains that can be achieved by use of multiple antennas, and which is one of the amongst the several gains, one of the most important gains that MIMO communication brings us. Now, in order to study such details, we would require some revision of concepts from information theory. So, this particular lecture would be dedicated towards revising some of the concepts which are fundamental towards building the expressions. The way we would like to do it is instead of giving the direct expression of capacity for MIMO systems, it is rather wise to start with the basics and do a build up of the capacity that is achieved for discrete random variable or discrete sources, and then move on to see how the capacity is achieved for the Gaussian channel. Once you are able to see that, then it is more or less straightforward that we will see what is the capacity in the case of multivariate Gaussian distribution. So, once we have that expression, then that would lead us directly to the case for MIMO communications, where all we need to do is use this build up, use the expression that we achieve when there is multivariate Gaussian distribution, and see how this maps to the MIMO system, where there are multiple antennas at the transmitter, multiple antennas at the receiver, and with one-to-one mapping we would be able to use almost the expression that is derived for multivariate Gaussian directly into the case of MIMO. So, that would ease our way of doing things, as well as it will give us an opportunity to understand how the expressions are as it is from the basics. So, with this, let us begin with some of the fundamental definitions that are used in arriving at the capacity expression for typical AWGN channel, which we will be exploiting later on. So, when we are talking of such systems, we are essentially talking about the digital communication system, and when we talk about digital communication system, we would like to begin with discrete sources. So, of course, when we go on finally, we would be reaching a situation where we have a waveform channel. So, in the beginning of this course, we had described how do you look at the channel, and at one point we said that the channel could be looked upon as a discrete input, discrete output, as well as it could be waveform. So, it is mathematically easier when you develop the discrete input, discrete output configuration, and then that could be translated to the Gaussian or the waveform channel. So, to begin with, let us take up discrete sources. So, when we look at a discrete source, we assume that there is a finite alphabet at the source. That means it has a set of symbols. One particular example could be the English alphabet along with a few punctuation signs. So, what we get in total, let us say there are 26 letters along with a few punctuation signs, so which keep on coming. The example we could take is if you would take a file which has English characters, and I would like to read them from the beginning. What I will be getting is the English letters from the English alphabet, as well as punctuations one after another. So, we can say that the source is generating random symbols, and because when we look at the output of one file from the other, or when we look at the sequence, there is no definite pattern unless it is premeditated. So, if it is not a premeditated, that means we want to inject a pattern. If we look at any particular text at random, the sequence of letters that would come out of it would be random in nature. So, when such things happen, it is often important to measure the randomness of the source. In this particular lecture, we do not intend to describe the how do you measure randomness or why do you measure it in this way in all details. We would like to directly give some definitions related to such sources, which finally build up towards measuring or towards defining how capacity is defined. And when we go down the course, we would also maybe giving you a prelude to how the capacity expression is arrived at, instead of giving the rigorous proof of the capacity expression, because here in this course our aim is to use the information theoretic capacity result, whereas a detailed derivation of the exact capacity expression is rather more appropriate in a course on information theory. So, with this background, we would prefer to look into the definition of entropy, which is one of the fundamental measures of randomness of a source. So, if we take that, let x be the outcome of the source. For instance, I take this English letters which are like A, B, C, D and so on. So, basically x1, x2. So, basically you have x1, x2 dot 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 as the outcomes. We can always associate a probability associated with each of the outcomes, p of x1, p of x2. So, for instance, that you look at the source which generates these English letters. So, if I take a file which has maybe 10,000 such letters, and then I try to make a histogram of the number of A's, the number of B's and so on, and I try to see a frequency plot, then what I can get is the probability of occurrence of A, probability of occurrence of B, probability of occurrence of C and so on and so forth. So, associated with each symbol there is a probability. With this there is a certain measure known as the entropy of the source. The entropy of the source gives you the inherent randomness in the source. So, we are again not going into details of description of this randomness, but rather the exact definition that which is useful for us. The entropy, as I said, is also useful in describing the average number of bits, zeros and ones, that would be required to encode the source in the most efficient way. In other words, it is the minimum number of bits that is required in order to encode the source. So for instance, we take these outcomes that are coming out, each with certain probabilities. So, given there is a symbol and there is a certain probability and there is a certain finite alphabet size, let us say x of n, entropy, which is usually given as hx, which we are going to define, is a measure of number of bits that we would assign on an average to each of these. For example, I could assign to A the bit sequence 0 1 0. I could assign to B the bit sequence 1 1 0 1 1. I could assign to C, for instance, 1 0 1 1 0 0. I could assign to D, for instance, 0 1 1 1 0 1. I could assign to E, for instance, 1 0 and so on, right. So, this is the bit sequence. So, this has a length of 3, this has a length of 1 2 3 4 5, this is a length of 4, this is a length of 3 and 3 6, this is a length of 2. So, the average of these would be, if I add them up and divide by 5, I am going to get the average bit length. So, what hx is going to give us is what would be the minimum value of the average number of bits per such symbol that could be used. So, that is the measure of entropy, and we all know what it is important for. One direct example of this would be it would give us information about what is the maximum amount of compression that could be done for the output of the sources. So, that is one way of using it, and of course, we are not going to use it in that sense over here. We are just going to look at entropy, because that is so fundamental that it will be used throughout until we arrive at the expression of capacity finally. So, hx is defined as minus sum of x element of the set which contains x, p of x log base 2 p of x. When you define it in log base 2, we would give the units as bits. So, as many bits are required. One could also define it as x element of big X, p of x ln natural logarithm p of x, and in this case the definition would go in nats. And in either of the case, we could see that we are taking px, which is greater than or equal to 0, and rather we would be interested in the case where p is greater than 0, and since it is a probability, this number is less than 1. So, px lies between 1 and 0. You could put an equal to, but we would prefer not to do it, because px equals to 0 means that does not occur. So, it is not part of the alphabet. So, if you would look at this, then log of px log of px is definitely negative. So this is less than or equal to 0 when px is equal to 1, and minus log px is greater than or equal to 0. So px is positive, log px is also positive. So that means this minus log px is also positive. So that means this whole number is positive. So we could say h of x is always greater than or equal to 0. So this is one of the fundamental things that we should always remember, that hx is never negative when we have x as the outcome of sources and px as the probability of occurrence of such sources. So, and remember, we are talking about a discrete random variable at this point of time. So this is what you would call the definition of entropy. Okay. So with this we move forward and define a few more terms that would be necessary in due course of time, and one of the next most important would be the joint entropy. The joint entropy of a pair of random variables x, y, which is a pair of random variables. So we would have h of x, y is equal to minus x element of big X, which is the whole set of that contains all the values of x, y element of big Y, which contains all y, joint distribution or joint mass function of p of x, y times log p x, y. In general, we will use log to indicate log base 2 or ln to indicate the natural logarithm. So this is the definition of joint entropy. The next important definition that we need is conditional entropy. So again, as said, we are not going to describe this much, but just give the definition. For joint entropy, briefly we could say that what is the probability, what is the entropy that two sources have a certain entropy together when there are two sources generating it. We could briefly talk in that sense. Conditional entropy, if given that means if we say that x and y are distributed according to p x y, then what is the conditional entropy? Conditional entropy H is denoted as h of y given x is the notation, which would be sum of x element of all of the set of x, p of x, h of y given x is equal to x. So this is the basic definition of conditional entropy of y. That means the entropy of y given x, entropy of y given x. So if we would proceed with this, what we get here is this particular expression, or we can write it again, h of y conditioned on x is equal to sum over x element of big of x px h of y given x is equal to x. So you are weighing this with the probability, and you could write this as x element of capital X, p of x, sum of this particular one. We could open it up saying it is y element of capital Y minus p of y given x log of p y given x. This is straightforward given the definition of entropy above. So if we look at the definition of entropy here, following that we could write this description, right. So going by this, we could write this as x sum over y element of all of x, all of y, p of x times p of y given x. There is a minus sign from here which comes out, log of p y given x. So this one is basically p of joint distribution of p of x and y, sum over y, sum over x, log p y given x. So this you could also write as minus expectation over the joint distribution of x and y log p y given x, log p of y given x, right. So this is what we could write. We could also have the chain rule following this. The chain rule says h of x y, the joint entropy is equal to h of x plus h of y condition of x. Now this could be done if you would write the left hand side as p of x y over all of x and y log p x y. Now p x y you could break it into p of x by Bayes theorem p of y given x. Now this is straightforward. You would have this multiplied by log p of x, right. So when this is added over y, you are left with minus summation. So we could rather do it. You would be left with minus xy px log px, right, and another term minus pxy times p of log p y given x, right. So this is p of x comma y. So this is basically when added over y, y goes out, adds up to 1. So this would be hx, and this whole term, as we have just seen, is basically h of y given x. So basically h of xy joint entropy is equal to entropy of one of them plus conditional entropy of the other with respect to the first. So this is also what would be useful. So with that, we move on further to talk about relative entropy. So again, we are giving a list of definitions which are important. Relative entropy, and we'll talk about mutual information. So when we talk of relative entropy, we would write this as the measure of the distance between two distributions p of x and q of x. It is also known as the Kullback-Leibler distance, and is denoted as p d of p with a parallel line between q. That means we are identifying the distance between the distributions. Now you can easily calculate distance between 2 points, but the distance between two distributions is not very easy to find. So there is a specific definition to it, and that is the particular definition that what we are looking at in this particular case. So when we look at the relative entropy or the Kullback-Leibler distance, this is given as x element of x p of x times log of px over qx, and this could be written as expectation over the density of p or the distribution of p times log of px by log of qx. And we would remember that we should remember this distance of p from q, the distribution of p from q as per this definition is not equal to the distance of the distribution of q from p. This is also fundamental. So using these definitions that we have used, we would now give the definition of mutual information, which is again fundamental in the expression of capacity. So the expression of mutual information when we look at it, we would consider two random variables x and y with joint mass function P of xy. See, we are talking about discrete random variables, therefore we are talking about mass functions and marginal probability mass functions. I would write in short functions in this way, P of x and P of y. So this is the notation that we have been using. The mutual information I of xy, it is denoted as Ixy, is the relative entropy. See, capacity is defined in terms of mutual information is defined in terms of relative entropy, and relative entropy is defined in terms of entropy. So all these things follow in suit, and therefore we have to develop one after the other. So the relative entropy between the joint distribution and the product distribution. So in other words, I of x y is given as sum over x element of all of x times sum over y element member of all of y, the joint over the P of x y. See, it is relative entropy between the joint distribution and the product distribution. So here if you look at it, distance between the two distributions px and qx, so it is given as sum over px log px by qx. So same thing follows over here, joint log p of x q of x divided by p of x times q of y, right? So between these two distributions, sorry, it's p of x times p of y. So basically if you look at this, it directly follows from the relative entropy, and between pxy and px times py. So it's basically the distance between the joint distribution to the product distribution. And some of the things you could get clear that this could be expanded easily as we could write in short as sum over xy. That means all of xy, we are writing in short all of xy pxy times log of px given y times p of y divided by p of x times p of y. P of y and p of y cancels. So with that we could write this further as this is equal to sum over pxy over all xy times, see, log is there in the px is in the denominator, so minus log px, because we have px in the denominator, log of px, so minus log px plus sum over all xy p of xy, that is p of xy times log of p x given y. So you can easily recognize this is basically h of x, and this is basically minus of h x given y. So this is what we have built earlier. So basically I x y could be written in terms of h x and h of x given y. In a similar manner we could expand this part into p, if we would write p of y given x times p of x times p of x times p of y. What do we get? These two we can cancel out if they are non-zero, and then I of xy, you can easily guess from this it will be h of y, and from this minus it will be h of y given x. So these are the definitions that we can follow, and if you would go by the chain rule, the chain rule tells us h of x y is equal to h of x plus h of y given x, or you could also write it as h of y plus h of y x given y. So this you could write it as h x plus hy minus of h of x y. So these are the three descriptions of mutual information which would be finally using that we can write. So here we can see that h of y given x is h of x y minus h x. So if we look at this one, h of y given x, so h of y given x is equal to h x y minus h x. So h x y minus, there is a minus sign, h x when comes to this side with the minus, minus and minus plus. So we have h x h y, and this term comes over here. So we have h x plus h y minus h x y. So we have reached an important point in our description of these important terms in terms of the entropy. So we started with entropy, we talked about joint entropy, conditional entropy, relative distance between the two distributions. Then we defined mutual information, which is again a very important term when we talk about capacity. So we conclude this lecture at this point, and we would look at some more definitions in the following lecture. Thank you.